Today we will learn field identification test. Standard practice for description and identification of soils. Scope of the test. The practice covers the procedure for the description of soils for engineering use. The identification is based on visual examination and manual test. It must be clearly stated in reporting identification that it is based on visual manual procedure. Standard reference ASTM D2488. Standard practice for description and identification of soils. Significance. The first step in any geotechnical engineering project is to identify and describe the subsoil condition. For example, as soon as a ground is identified as gravel, engineer can immediately form some ideas on the nature of problems that might be encountered in a tunneling project. In contrast, a soft clay ground is expected to lead to other types of design and construction consideration. Therefore, it is useful to have a systematic procedure for identification of soils, even in the planning stages of a project. Soils can be classified into two general categories: 1. Coarse-grained soils and 2. Fine-grained soils. Usually, coarse-grained soils are sand, gravel, cobble and boulder, while fine-grained soils are silt and clay. Procedures for visually identification of fine-grained soils are described in the following sections. Apparatus required: spatula, wooden hammer, beaker, glass rod stirrer, 1/8-inch dia steel rod. Identification of peat: a sample composed of primarily of vegetable tissue in various stages of decomposition that has a fibrous to amorphous texture, usually a dark brown to black color, and organic order shall be designated as a highly organic soil and shall be identified as peat. Preliminary identification. Soils can be classified into two general categories: 1. Coarse-grained soils and 2. Fine-grained soils. Examples of coarse-grained soils are gravels and sands. Examples of fine-grained soils are silts and clays. Procedure for visually identifying these two general types of soils are described in the following sections. The soil is fine-grained if it contains 50% or more fines. The soil is coarse-grained if it contains less than 50% fines. 1. Identify the color. Example: brown, gray, brownish gray. Order, if any, and texture, coarse or fine-grained, of soil. 2. Identify the major soil constituent greater than 50% by weight using table 1.1 as coarse gravel, fine gravel, coarse sand, medium sand, fine sand or fines. 3. Estimate percentages of all other soil constituents using table 1.1 and the following terms: trace 0 to 5% by weight, few 5 to 10%, little 15 to 25%, some 30 to 45%, mostly 50 to 100%. Examples: trace fine gravel, little silt, some clay. Table 1.1 Grain size distributions. Engineering properties of soils based on laboratory testing. Soil constituent: boulder. Size limits: 12 inches, 305 mm or more. Familiar example: larger than basketball. Soil constituent: cobbles. Size limits: 3 inches, 76 mm to 12 inches, 305 mm. Familiar example: grapefruit. Soil constituent: coarse gravel. Size limits: 3/4 inches, 19 mm to 3 inches, 76 mm. Familiar example: orange or lemon. Soil constituent: fine gravel. Size limits: 4.75 mm, number 4 sieve to 3/4 inches, 19 mm. Familiar example: grape or pea. Soil constituent: coarse sand. Size limits: 2 mm, number 10 sieve to 4.75 mm, number 4 sieve. Familiar example: rock salt. Soil constituent: medium sand. Size limits: 0.42 mm, number 40 sieve to 2 mm, number 10 sieve. Familiar example: sugar, table salt. Soil constituent: fine sand. Size limits: 0.075 mm, number 200 sieve to 0.42 mm. Number 40 sieve. Familiar example: powdered sugar. Soil constituent: fines. Size limits: less than 0.075 mm. Number 200 sieve. Particles finer than fine sand cannot be discerned with the naked eye at a distance of 8 inch 20 cm. 4. If the major soil constituent is sand or gravel, identify particle distribution. Describe as well graded or poorly graded. Well graded soil consists of particle sizes over a wide range. Poorly graded soil consists of particles which are all about the same size. Identify particle shape: angular, subangular, rounded, subrounded, using figure 1.2 and table 1.2. Figure 1.2 shows you shapes of coarse-grained soil particles. Description: angular. Criteria: particles have sharp edges and relatively plain sides with unpolished surfaces. Subangular: particles are similar to angular description but have rounded edges. Subrounded: particles have nearly plain sides but have well-rounded corner and edges. Rounded: particles have smoothly curved sides and no edges. 5. According to the major soil constituents, perform the following tests. Procedure for identifying coarse-grained soils: gravel, sand, and fines. 1. The percentages of the following particle fractions are estimated. 1. Gravel fraction: 75 mm to 4.75 mm, or approximately 5 mm. 2. Sand fraction: 4.75 mm or 5 mm to 75 micron. 3. Soil fines, that is silt and clay fraction, smaller than 75 micron. According to USCS followed by USBR USA, Army Corps of Engineer ASTM and ASCE, range of silt size is 0.002 mm to 0.074 mm, and clay particles are smaller than 0.002 mm. 2. If the gravel fraction is greater than sand fraction, identify the soil as gravel, capital G. The gravel fraction may be further divided into: first, coarse gravel 75 mm to 20 mm, and second, fine gravel 20 mm to 4.75 mm. 3. If the gravel fraction is equal to or less than the sand fraction, identify the soil as sand, capital S. The sand fraction may be further divided into: first, coarse sand 4.75 mm to 2 mm, second, medium sand 2 mm to 425 micron, third, fine sand 425 micron to 75 micron. 4. Identify the soil further as clean gravel or clean sand. If the percentage of fines is estimated to be less than 5%, identify it as gravel with fines or sand with fines if the percentage of fines is estimated to be more than 15%. 5. Classify the clean gravels or clean sand as follows. Identify the soil as well-graded gravel GW or as well-graded sand SW if there is good representation of all particle sizes. Identify the soil as poorly graded gravel GP or as poorly graded sand SP if it contains predominantly of one size, uniformly graded, or it has a wide range of sizes with some intermediate size is obviously missing gap graded. 6. Classify gravel with fines or sand with fines as follows. A. If the other coarse grained constituent is less than 15%, then silty gravel GM or silty sand SM if the fines have little or no plasticity, or clay gravel GC or clay sand SC if the fines are of low to medium or high plasticity. B. If the other coarse grained constituent is greater than 15%, then the group name shall be a combination from the two columns below. Silty gravel with sand, clay gravel. Silty sand with gravel, clay sand. 7. If the percentage of fine is in between 5 to 15%, then the group name shall be a combination from the two columns below. Well graded gravel with clay. poorly graded gravel with silt, well graded sand, poorly graded sand. Boundary classifications. Assume the coarser soil first. When there is a choice, complete the classification and assign the appropriate symbol. Then, beginning where the choice was made. Assume the finer soil, complete the classification and assign the second group symbol. The examples are as follows. Field identification of fine-grained soils, silt and clays. Select a representative sample of the material for examination. Silt and clay particles are not visible to naked eyes. The amount of silt and clay in a soil sample can be identified by the following field tests: dispersant test, dry strength test, dilatancy test, shaking test, water mobility test, plasticity test, toughness test. 1. Dispersant test. A small quantity of the collected soil sample is dispersed or mixed with water in a glass cylinder or test tube or beaker and then allowed to settle. Silt particles usually settle in 15 to 60 minutes, whereas clay particles will remain in suspension for at least several hours or may remain even for several days. If some sand particles are present in sample, then it settles in 30 to 60 seconds. Figure 1.3 shows you dispersion test. 2. Dry strength test. At first the soil samples are molded, then prepare 4 or 5 pads from this molded sample, about 25 mm in diameter and 6 mm in thickness. Dry all the pads completely either naturally or in an oven. Measure its resistance to crushing between the fingers. This resistance, called the dry strength or crushing strength, is a measure of the plasticity of the soil. Crushing of dry clay lumps is relatively difficult, whereas silt lumps break quite easily. Test the strength of the dry pads or lumps by crushing between the fingers and note the strength in accordance with the criteria in Table 1.3. Table 1.3 shows you dry strength test, engineering properties of soils based on laboratory testing. Description: none. Criteria: the dry specimen crumbles into powder with mere pressure of handling. Description: low. Criteria: the dry specimen crumbles into powder with some finger pressure. Description: medium. Criteria: the dry specimen break into pieces or crumbles with considerable finger pressure. Description: high. Criteria: the specimen cannot be broken with finger pressure. Specimen will break into pieces between thumb and hand surface. Description: very high. Criteria: the specimen cannot be broken between the thumb and hard surface. The presence of high-strength water-soluble cementing materials such as calcium carbonates may cause exceptionally high dry strength. The presence of calcium carbonate can usually be dilated from the intensity of the reaction with dilute hydrochloric acid. 3. Dilatancy test. From the specimen, select enough material to mold into a ball about 0.5 inch in diameter. Mold the material, adding water if necessary, until it has a soft but not sticky consistency. Smooth the soil ball in the palm of one hand with the blade of a knife or a small spatula. Shake horizontally, striking the side of the hand vigorously against the other hand several times. Note the reaction of water appearing on the surface of the soil. Squeeze the sample by closing the hand or punching the soil between the fingers, and note the reaction in accordance with the criteria in Table 1.4. Table 1.4 shows you dilatancy test, engineering properties of soils based on laboratory testing. Description: none. Criteria: no visible change in specimen. Description: slow. Criteria: water appears slowly on the surface of the specimen during shaking and does not disappear or disappear slowly upon squeezing. Description: rapid. Criteria: water appears quickly on the surface of the specimen during shaking and disappears quickly upon squeezing. 4. Toughness or plasticity test. Following the completion of the dilatancy test, the test specimen is shaped into an elongated pad and rolled by hand on a smooth surface or between the palms into a thread about 1/8 inch in diameter. If the sample is too wet to roll easily, it should be sprayed into a thin layer and allowed to lose some water by evaporation. Fold the sample threads and re-roll repeatedly until the thread crumbles at a diameter of about 1 by 8 inch. The thread will crumble at a diameter of 1 by 8 inch when the swirl is near the plastic limit. Note the pressure required to roll the thread near the plastic limit. Also note the strength of the thread. After the thread crumbles, note the toughness of the materials during kneading. In a word, it is expressed as clay can be rolled out into small threads about 1 by 8 inch thickness, whereas silt is much more difficult to roll into small threads and generally requires more water. Figure 1.5 shows you toughness and plasticity test. Table 1.5 Toughness test of plastic thread. Description: low. Criteria: only slight pressure is required to roll the thread near the plastic limit. The thread and the lump are weak and soft. Description: medium. Criteria: medium pressure is required to roll the thread near the plastic limit. The thread and the lump have medium stiffness. Description: high. Criteria: considerable pressure is required to roll the thread near the plastic limit. The thread and the lump have very high stiffness. Table 1.6 Plasticity test. Description: non-plastic. Criteria: a 1 by 8 inch thread cannot be rolled at any water content. Description: low. Criteria: the thread can barely be rolled and the lump cannot be formed when drier than the plastic limit. Description: high. Criteria: it takes considerable time rolling and kneading to reach the plastic limit. The thread can be rolled several times after reaching the plastic limit. The lump can be formed without crumbling when drier than the plastic limit. Combining all four field test results. Table 1.7 Field identification of fine-grained soil. Typical name: sandy silt, dry strength, none to very high, latency reaction, rapid, toughness of plastic thread, low, time to settle in dispersion test 30 seconds to 60 minutes. Typical name: silt, dry strength, very low to low, latency reaction, rapid, toughness of plastic thread, low, time to settle in dispersion test 15 to 60 minutes. Typical name: clay silt, dry strength, low to medium, latency reaction, rapid to slow, toughness of plastic thread, medium, time to settle in dispersion test 15 to several hours. Typical name: sandy clay, dry strength, low to high, latency reaction, slow to none, toughness of plastic thread, medium, time to settle in dispersion test 30 seconds to several hours. Typical name: silty clay, dry strength, medium to high, latency reaction slow to none, toughness of plastic thread, medium, time to settle in dispersion test 15 minutes to several hours. Typical name: clay, dry strength, high to very high, latency reaction none, toughness of plastic thread high, time to settle in dispersion test several hours to days. Typical name: organic silt, dry strength, low to medium, latency reaction slow, toughness of plastic thread low, time to settle in dispersion test 15 minutes to several hours. Typical name: organic clay, dry strength, medium to very high, latency reaction none, toughness of plastic thread high, time to settle in dispersion test 7 hours to days. Table 1.8 Identification of inorganic fine-grained soil. Soil symbol ml, dry strength none or low, latency slow to rapid, toughness low or thread cannot be formed. Soil symbol Cl, dry strength medium to high, latency none to slow, toughness medium. Soil symbol Mh, dry strength low to medium, latency none to slow, toughness low to medium. Soil symbol Mh, dry strength low to medium, latency none to slow, toughness low to medium. Soil symbol Ch, dry strength high to very high, latency none, toughness high. Note: Ml is equal to silt, Cl is equal to lean clay, low plasticity clay, Mh is equal to elastic soil, Ch is equal to fat clay, high plasticity clay. The terms lean and fat may not be used in certain geographic regions. Midwest. Table 1.9 Criteria for describing soil moisture condition. Description: Dry. Criteria: soil is dry to the touch, dusty, a clear absence of moisture. Description: Moist. Criteria: soil is damp, slight moisture, soil may begin to retain molded form. Description: Wet. Criteria: soil is clearly wet, water is visible when sample is squeezed. Description: Saturated. Criteria: water is easily visible and drains freely from the sample. 5. One moistens a spot on the soil and rubs a finger on it. If the rubbed spot appears smooth, the material is clay, but if it appears scratched, it is silt or silty.